of course. So let's go to our next speaker, Konstantin. Konstantinos.
Yes, and I'm sharing my screen as fast as I can.
Okay, thank you very much. I apologize.
No problem at all. So thank you for the opportunity to speak here today. I'm going to discuss a time variable quantization model and how we can use that to probe the evolution of the corona, as many people discussed before me already. So let me go ahead right away. When we discuss quantization, at least semi-analytically how we do it, we need an input source. And in our case, that is the accretion disk, of course, which can be modeled as a multicolor black body. And what happens is that once we use a kernel for quantization, which can be, for example, the component equation, which is actually a partial differential equation that tells us how the green spectrum that I saw there on the left changes with time in different energies to lead to the red curve, which is the quantized spectrum. And if one would like to visualize it geometrically, the simplest picture which we use in our model is actually an accretion disk, which is depicted here as the light blue cone, and a spherically symmetric extended corona around it. And what we call the steady state spectrum is the soft spectrum initially emitted from the disk, scattered multiple times inside this extended corona, and obtained at the outer edge of the corona as the time average spectrum. The simplest way to approach time variable quantization, especially in coherent variability, is by saying that, okay, we know that the output spectrum oscillates quasi-periodically, actually. And so if we trace that back into the corona, that means that there should be an oscillating photon density inside the corona, which is scattering off of the electrons. Now, this spherical corona has a temperature TE, an optical depth tau, and a size L, since we assumed it's spherical. And if we now assume that the photon density that is being quantum scattered inside is oscillating, then it is fair to assume that the temperature of the corona is also oscillating. And this is why I've used those red deltas here in N gamma, which is the photon density, and TE, which is the corona temperature. And also, by random walk arguments, some of the flux, fraction of the flux, will go back to the disk, and we call that feedback. I write that with an eta. And since this is also going to be oscillating, it is going to induce an oscillation to the disk. And this is why I have a delta on the temperature of the disk, the inner temperature of the disk. Now, note that we don't really say which one of those mechanisms is driving the variability. It could be oscillations in the temperature of the disk that actually drive the flux to be oscillating inside the corona. And as a result, the temperature of the corona oscillates, or the other way around. Since we're also treating the time-dependent problem, we also need an external heating rate here to match the cooling of the corona in those timescales. And if we put all those components back into the quantizing kernel, which is the components equation, we can solve actually for this delta and gamma, which is a complex quantity. And from that, we can get an RMS and a time lag. So given a set of the 5 parameters that we have here, temperature of the corona, optical depth, size, temperature of the disk, and feedback efficiency, the eta, we can get the time lag or phase lag and the RMS in any energy band that we want. And now let me quickly switch to data and how we can apply this model. I'm going to talk only about GRS 1915, which have been well studied from RxT. And what I saw here, the plot on the left, is the phase lag versus frequency relation, which have been pointed out by many, many authors in the past. I have a few here. And this data set here is the most comprehensive to date from Zhang et al. 2020. And it shows how the lags switch from soft or negative at low energies to positive or hard at lower QPO frequencies. This is a type C QPO, by the way. And this switch happens at around 2 Hertz, more or less. And what we have done as a first step is, since our model can actually not fit this relation here, because we have 1 measurement of phase lag and 5 parameters for the model, what we can do as a first step is populate this 2D diagram here and see whether our simulations that actually cluster alongside the blue dust line, which is actually the best fitting broken law here. It's basically an empirical relation. Whether those models, those simulations that cluster along this line give a particular dependence of the model parameters upon QPO frequency. So what we're trying to answer actually is why are the lags switching from negative to positive? And what we find here, the plot on the left shows how the size of the corona, this extended corona, changes as a function of QPO frequency, and the bottom shows the feedback efficiency, how the feedback efficiency changes as a function of QPO frequency. And as you can see, moving from right to left, the top panel, the extended corona decreases in size from about 100 Rg to around 10 at about 2 Hertz. And the feedback efficiency is very high, actually 100%. And that means that 100% that the disk is actually dominated by Comptonized photons that impinge back on it. And suddenly the feedback efficiency drops abruptly around 2 Hertz to less than 5%. And that is relatively natural in this very simple scenario that we have in this very simple model. If we assume, and now if you look on the right, you see at the geometry of the corona and the accretion disk, when the QPO is at around 6 Hertz, and then when the frequency decreases, the corona decreases as well, and is covering less and less of or interacting less and less with the accretion disk. And at some point, those two become more or less detached, or at least they have the minimum, the feedback will get the minimum efficiency. But what the model tells us, and this comes from the hard lags at very low energies, is that the size of this extended corona needs to increase again to explain the hard lags at very low frequencies, while the feedback efficiency stays quite low again. Now, the next step is that we can actually go ahead and now fit energy-dependent spectra. And here on the left, I show the fractional RMS of the type C QPO, and on the right, the time lag as a function of energy now. These are selected observations from Zhang et al. 2020. And now we can actually constrain all the parameters. We can actually fit the model and constrain all the parameters that I mentioned before. And these are typical fits, but what we actually did was fit all 400 plus lag energy spectra from Zhang et al. 2020. And this is going to be shown in an upcoming publication from Federico Garcia. And what we show here is that now by fitting the energy-dependent RMS and time lags, the size indeed systematically decreases. The scale is different here, so apologies for that, until 2 Hertz. And the feedback, as you can see, which is actually the color of each point, is the feedback efficiency, again, drops abruptly when the frequency goes to around 2 Hertz and stays low as the QPO frequency decreases further and the size increases again. So to conclude, I have 2 main points, and one is that modeling the variability through Comptonization allows us to constrain geometrical parameters that are otherwise inaccessible, and these are the size and feedback efficiency, at least with this model, with this particular model. And we have used the most comprehensive or most inclusive timing analysis for GRS 915 so far, and we show that the switch of the lags from soft to hard at around 2 Hertz can actually be explained by a corona, an extended corona that is first decreasing in size and then increasing after, below 2 Hertz, while the feedback efficiency is consistently decreasing. So that will be all, and I hope that, thank you very much for your attention, and I hope I made it a bit shorter.
Oh, thank you. I really appreciate it because we were running a little bit late,
No problem.
but that was very useful. One panelist raising the hand.
Sorry for not starting my video.
That's okay. Yeah, okay. Yeah, Phil.
Yeah, so what I'm curious about is in the lags, if you look at the lag versus frequency in GRS 1915, the evolution, when it goes through 0, it also it's basically a log linear relation between the lag and frequency. It's a very tight log linear relationship. So this is like in Pablo Reich's work, but also other works as well. And so it seems curious to me why that would be, that with a log linear relation with the same gradient on both sides of zero, if you have this kind of discontinuity in the properties in the evolution of the corona. So I just wondered if there's a way that you could explain that. Is it a coincidence, or is it a feature of the model that it would explain the log linear dependence?
No, I think it's a feature of the model, and it has to do with how the once you change the feedback, let's say from positive or something to zero or to very low, then those relations, the fractional RMS and the time, like particularly the energy dependence, change very fast. They don't change smoothly. They change very abruptly, the energy dependence, and so also the integrated quantities or the band integrated quantities that you calculate will also change rapidly. So I think it is a model-dependent feature.
But how would it arise? Because surely the parameters of the lag are dependent on the parameters you're fitting. So you're fitting the model and getting these parameters. But you'd want a first principles physical prediction that said those parameters evolve in a particular way to make the lag go through with a log linear law straight through the zero with the same gradient the other side. That's what I don't really understand about it, that it just seems like a weird coincidence, given that you're fitting each QPO frequency to get these parameter variations.
Sorry, but now you're referring to this plot, right?
Yeah, but so if you plot it on a log linear relation, you'll see it's just a really tight log. I mean, it's remarkable how tight the relation is. Like, you can look at this in previous papers. So I've always found that one of the most peculiar properties of the 1915 lags, and that's why I think it suggests some sort of continuous process. I have no idea what, rather than some sort of changes really in distinct changes in the structure.
Yeah, well, I have to think about that. It's interesting, but but we know why, at least in the model, we have this abrupt change around 2 Hz, and that is purely driven by the feedback. So maybe we have to, I have to think that, well, there is a problem with feedback is that you can actually, you don't have to have it as a free parameter to the model. You can actually constrain it from geometrical properties, from the geometry of the system. And we are trying to do that at some point, but yeah, that could be a game changer. I will see.
Thanks.
No problem.
All right. Thank you.
May I ask a question, Emrah?
Yeah, of course. Go ahead.
So let's go to the last figure you have now. The size of the corona decreases with increasing frequency, QPO frequency. That sounds very understandable to me. But then it starts increasing again, even though the QPO frequency goes up. Yes,
that's a very interesting question. And I don't know if you noticed, but I saw here that the inferred size from the data increases, but which means that the size of the corona increases, and it should, in principle, cover the disk. So the feedback efficiency should go high, but it doesn't. It stays low. At least this is what the data says. And this is it might be viewed as a self-inconsistency. But what that might mean is a change in the geometry. So the geometrical assumptions that we have that lead us to get a very big size at low frequencies because of the data.
Okay, let me just interrupt. In general, I tend to find high frequency, small radii. So we see at the beginning that in the start of the figure that a low frequency, large size, then reaches a minimum, then the frequency keeps going up. Well, we don't quite understand why the frequency goes up. Maybe you do, and in which case I have to understand it. You have to explain to us. But then the corona goes up again. Why? Because the lags? Is that what why you find that the corona gets larger?
Yes, that is driven from the lags and the high feedback efficiency.
So the lags get longer, basically, even though the frequency of the QPO goes higher, the lags become longer?
Yes, but they are soft lags. They are not hard lags now.
Okay.
And we interpret that by the fact that the disk has to receive enough hard flux from the corona, which is already big enough, to actually thermalize to a higher temperature and then re-emit this temperature as another black body.
But the soft lags may very well mean that simply, let's see, the soft lags means that they soft lag the hard. Is that the idea?
Yes. But the hard photons are emitted first.
That is generally explained as, well, okay, as the response. Okay, well, I don't know. We have to. Okay, thank you.
It is indeed a complicated discussion. Yes.
All right, I have to read your paper. Thank you.
Yes,
Thank you
please.
very much.
Let's move on to Mariano Mendes. I am really happy that these discussions are taking place, but that can go on. We're running a little bit tight on time, so